Alright guys, this is part two of my amount of substance revision. So I'm going through the physics and maths tutor. If you remember, I told you about this website. This is the physics and maths tutor website. Oh my days, this dude here, he charges £500 an hour. Anyway, if you click on physics and maths tutor, you go to AQA, A-level chemistry, and just looking at the recent papers 2016 to 2021, which is the relevant curriculum for everyone doing A level at the moment. If you click on amount of substance, they've also got the mark scheme there. Anyway, I'm going through this pack. Okay, so I'm going to try and get through some more questions in this lesson for amount of substance. It's an important topic to do because some of you guys are studying this right at this moment. You're doing moles, amount of substance. You're probably also doing atomic structure, so I might do something on that at some point. Anyway, let's get into it. Yeah, let's get into the chemistry.
This time for
chemistry.
yeah, baby.
All right. Now, this is an ideal gas equation. So, what's taking place here is we basically got a gas syringe here going on, and I'm going to move my face in a minute because it's right in the middle of the exam paper. But let's have a little look. I'll talk you through the question first of all. The question is about a volatile liquid A. Just get rid of that. What's going on there? Oh, days. So Norton decides to do a scan right now. Oh, don't even read that. Yes. Go. I don't want that. Yikes. Yeah, what's going on? Hold on, I'm just testing this up here, people. Wait a second. Just making sure everything is working, because right now I can't see jack. What's going on? Let me just check. Okay, yeah. All right, we're going. I don't know, man. I'm watching the stream on my mobile, and sometimes it doesn't even tell me what's happening. All right, we're going to go through this. First question is on the ideal gas equation, so let's go. Now, this question's about volatile liquid A. Just highlight the key points. Make sure you always highlight. We want to find the relative molecular mass, so the MR is what we're going to be looking for. It says an experiment was done to find the molecular mass, the MR. A student injects a sample of liquid A into a gas syringe in an oven, so we're heating it here in this oven, and we've got a gas syringe to measure the volume of the liquid once it vaporizes. Okay, and then down here we've got some information. Whoa, what is that? Highlight pen. Looks like we've got mass. So I'm already thinking mass moles. Should already be thinking that. We've got a volume given here, centimeters cubed. We've got pressure. And it looks like we've got temperature. And then if I shrink my face down and move it, I'm going to move it over to gas oven. We don't need that bit of information for this question. So if I move myself over here, super duper, right? We've also been given calculate the MR of A. So as suspected, the aim of this question for 4 marks is to calculate the molecular mass. So that was a bit deep, that blue. There we go, a little bit better. Give the answer to 3 significant figures. So this is key, why you should always highlight, because that's something people will miss and then they'll lose a really easy mark. Remember, the grade boundaries for A-level chemistry are pretty high, so you're going to need all the marks you can get. You can't be affording to drop easy marks. And then we've got the gas constant, R equals 8.31. So this should trigger, hey, ideal gas equation. The thing is, do you remember the equation for the ideal gas equation? So in your head, just see if you can remember it. If you don't remember the ideal gas equation, you're going to really struggle to get the marks. So it's a given at A level that you need to learn these equations off by heart. You can't do what you did at GCSE and be a bit lazy with learning the equations. You need to get the equations on your wall, get them on post-it notes around your room where you're studying, and get learning those. So by year 13, by the end of the course, you know the equations off by heart. Very, very important to learn your
Remember.
Equations. All right. Now
yeah. The equations are important. Listen to Michael. Right, here we go. Ideal gas equation. PV, should know this, and that is equal to nRT. Now, obviously, R's been given to us here. So we now know PV equals nRT. What we need to be thinking about here is how to rearrange this. So we're going to want to rearrange this equation so that we can make n the subject. Obviously, we need to find n because they're asking us for MR. And the other equation you're going to need to know off by heart, you should know from GCSE. If you got onto A level without knowing this off by heart, then something's seriously wrong. You need to know moles times MR is mass, and they gave us mass down here, so we definitely know we need that equation, and we're going to need to work out the moles here so that we can find the MR using the mass. So let's first of all rearrange this, and you should know how to rearrange that to make n the subject. So your next port of call is to rearrange this, and you do that by leaving n on one side and removing everything else. Now, as n is times multiplied by RT, we can divide both sides by RT, and that cancels out the multiplication of RT on the right, and it adds a divide RT on the left. So now we've got our equation rearranged so that n is the subject, number of moles. So that's step one. Step two with these ideal gas equations is get your conversions down. Okay, we want to write all the numbers in, but we've got to do our conversions. Let's start with pressure. Remember, so pressure is our first part of our equation. It says 100 kilopascals. So you need notes. When you write your ideal gas equation, you stick it on the wall of your bedroom. You need to have notes. By the way, kilopascals is, you need to know that it's in pascals. Okay, you just got to remember for this equation, you're going to be doing, instead of 100 kPa, we're going to turn that to 100,000. Remember, the K stands for 1,000 kilo. So our pressure is 100,000. Now we need to multiply that by the volume V. So V is over here, and V, well, it says it was 0 at the start. Obviously, we hadn't injected any gas into the syringe, and afterwards it was 178. But again, volume, when we're dealing with moles and concentrations, we do it in decimeters. But in the ideal gas equation, we use meters cubed. Okay, so we need to divide 178 by a million. And in order to do that, you're going to do 178 divided by 1 times 10 to the power of 6, which is a million. And what you'll get is 1.78 times 10 to the minus 4 when you do that. So you can check that in your calculator. You should get 1.78 times 10 to the minus 4. Now we're going to divide that by RT. Now you'll never have to convert R. It's just 8.31. You will know that off by heart very quickly into the A level. It's like the old 9.8 or the specific heat capacity of gravity, or the specific heat capacity at GCSE, the 4.18 or whatever. You kind of learn that one off by heart, so don't worry about that. Our temperature over here is in degrees Celsius. We need to change that to Kelvin, so it's very important in the equations that chemists use Kelvin. So we're going to plus 273. If you plus 273 to 120, we're going to get 393 Kelvin. And when we carry out this sum, that's going to give us the moles. So let's smash this in the calculator and do a bit of calculation, and you should come up with an answer that is 0.00545. Oh, my 4's not working very well, and that's the moles. Okay, so that is our moles. of the substance, of the gas that's inside the syringe. So you probably scored yourself 2 marks here. I know, all that work. 1 mark for the equation. Normally you get 1 mark for rearranging the equation and 1 mark for the conversions. Okay, they may even give us a third mark for the moles, but we now need to do mass over MR. And look down here, you can work out the moles by taking the initial mass and subtracting the mass after injecting, and we can work out the grams that have gone in. So if we do 11.295 and we minus 10.835 grams, we're going to get 0.46 grams. So the mass is 0.46. There's the work in there. And what do we need to do? We need to do this equation here. Mass over N equals MR. So we're going to go 0.46 divided by 0.00545. And what we should get, let's check it out in the old calculator, 0.46 divided by 0.00545. Okay, we get 84.4036, but we need to do this to 3 significant figures, and it's dead easy peasy because 84.0, so we just 84.4, and there's our 3 significant figures, and that would score you maximum marks. So you have the working out now. So 1 mark for the conversions, 1 mark for rearranging the equation, normally 1 mark for moles. I'm surprised it's only 4 marks. Normally 1 mark for carrying out the equation, but a mark for mass over moles, and then a mark for the significant figurage. Right, next question. The student noticed that some of the liquid injected into the gas syringe did not vaporize. So some of the liquid that they fired into the gas syringe, which my face is over, did not vaporize, didn't turn into a gas. Explain the effect on the MR that we've just calculated, the 84.4. What would be the effect if not all of the liquid vaporized? Well, if not all of the liquid vaporized, what would happen to the volume inside the gas syringe? So we would have a decrease in volume as less gas. Okay, so we've got less gas in there, so we've got a decrease in volume. Now if you think that the volume was on the top, that was the PV, we've got P times V. So if you decrease the number on top, you're going to get a smaller amount of moles. Okay, you can show that if you're kind of getting stuck in an exam and thinking, oh, what would happen, what I would recommend is doing a little right. Like imagine I had 10 over 2, that would be 5. Imagine the 10 is P times V and the RT is 2, then that would equal 5. 5 would be my number of moles. But let's see what happens when we decrease the top number. So let's say we decrease the top number to 5. So the P times V, because the volume went down, is now 5. What happens to the moles? It equals 1. So it's caused a decrease in our moles. Oh, sorry, hold on. Why did I divide by 5? That's a bit dumb. We should divide by the same thing. So 5 divided by 2 is 2.5. Anyway, you get the idea. If we halved our volume, if we half the number on top, our pressure times volume, we're going to get half the amount of moles. Moles are going to go down. So you're just doing a simple mental maths calculation will help you follow through what would be the consequence of decreasing one of these. Now, if the moles go down, so we're going to say less moles. If you had less moles when you come to the next calculation, so you got your 0.46, but instead of being over 0.00545, let's reduce that and say, we're just making these numbers up. You don't need any of these numbers. These are just to show to you how when you're in an exam under pressure, you can just put some numbers in and find out. So it was 0.005. Let's put in 0.002. Okay, so we've decreased it from 0.00545 to 0.002. Let's see what happens. You should be able to work out what's going to happen. we're going to get 230. So what does that mean? That means the MR will go up. So I've just put those random numbers in just to show you that you can use a bit of exam technique in the exam. The best time to use exam technique is in the exam, obviously. If you use good exam technique, you can see these would be the answer. You don't need to put the numbers. Decrease in volume as less gas, so the MR increases. That would be all your marks. A decrease in volume, decrease in moles, so an increase in the MR. But if you have to check what would happen, just plug some numbers in and see what would happen when you change some of those numbers. All right, cool. Probably time to move on and do another question. So let's go.
Keep moving on, keep moving on, keep moving on, keep moving on.
Right. I'll say that it's the same question. Okay. Right, so we've got the same data here. This is a second part to the same question. Quick mic check. Right, each reading on the balance used to record the mass of the fine needle. Okay. So, we've been given an uncertainty here of plus 0.001. If you can't see that, let me just put the uncertainty. So uncertainty, I need to move my face. Let's go face. Right, now you can see the question. Uncertainty is 0.001 grams. I'll do something on uncertainty at some point of why you get uncertainty, but in every measurement you make in chemistry, when you're measuring volume in a burette, when you're measuring mass on a scale, whatever you're measuring, gas in a gas syringe, there will be uncertainty. There'll be some error there, which is natural in any measurement humans ever make. So it's telling us that the uncertainty measurement is 0.001 for each measurement. Calculate the percentage uncertainty in the mass of liquid A injected in this experiment. Well, look, we've got two readings. We took an initial reading, the mass of the fine needle and syringe before injecting. Okay, so before we injected and then after we injected. So we took two readings. That means we got uncertainty here. We got some uncertainty. That could be out by 0.001 gram. And guess what? This reading could be up or down, plus or minus 0.001 gram as well. So our total uncertainty is 0.002 grams. You can put the little plus or minus if you really want. You don't need to do that. Now, this is another equation that you guys need to know off by heart. You kind of did this in GCSE, but you need this for A-level biology, A-level chemistry, A-level physics. The percentage uncertainty is the uncertainty in a measurement divided by the measurement times 100. So just make sure that you learn your equations off by heart. Mega important that you write these down as you come across them, stick them on your wall.
Remember.
Equations. All right. Now
Okay. So we write this over the top of the measurement. The measurement, what was the measurement? So our measurement was 0.46. So we're going to divide this. I don't know what I've done there. 0.46. That's the mass of liquid that was injected. We found that out by the minusing the original mass from the mass after. We found out how much liquid was injected, but there was some error there. So you're going to carry out this times 100. Let's see what that equals. So 0.002 on the old calculator divided by 0.46 equals that times 100 equals 0.347. I'm going to round that up. So does it? Yeah, 0.34543. Oh gosh, what have I done? I missed out a 4. That was a bit disastrous. Let's rewrite that. Let's type that. I seem to make less errors when I type. 0.435, and that's percent. Boom. So awesome. Let's move on to the next question. Right. Now, this question is: a student investigates two experimental methods of making methyl propanol. The equations for these two methods are shown. Method 1, we have a molecule, we're not interested in its name, MR is 116, and it forms some products with an MR of 72. And then we have a second method of making the same product, which also obviously has an MR of 72, but this time we've used a different reaction. What they have here is a little table with two missing bits of information. For each method, they've calculated the yield in milligrams, sorry. And they have the percentage yield, and we also have the atom economy. So this question for 6 marks essentially is asking us to calculate the percentage yield for method 1 and the atom economy for method 2. So percentage yield is another equation. So for percentage yield, you want actual mass, and you would have done this at GCSE, over theoretical mass times 100. So how do we work out? We know what the actual mass is because we have it here. So the actual mass is 552 mg. Now, let's get rid of that. 552 mg. Do you know what that is in grams? What is 552 micrograms into grams? So what you want to do is you want to divide by 1,000. When you're going up the scale, you divide by 1,000. So if you're going from micrograms to grams, divide by 1,000. Just like if you were going from meters to kilometers or joules to kilojoules, you divide by 1,000. So this would be 0.552 grams. So we have our mass. That is the actual mass. We now need to calculate the theoretical mass, because then we can divide this by the theoretical mass to get the percentage yield. How are we going to work out the theoretical mass? Well, we know that we have an MR of 116. Okay, in each method the student used key bit that need to highlight. The student used 1 gram of organic starting material. So let's work out how many moles we've got and how many moles we should get of our product. Kind of like a GCSE reacting mass question. So over here I want to do 1 gram, which is mass, divided by the MR, 116 for the MR, and that's going to give me the moles of my starting product. And I've got 0.0086 moles. Okay, so that's how many moles of my starting product I've got. We can see this is a one-to-one reaction. You might say, how can you see it's a one-to-one reaction? Look, there's no numbers in front. So there's 1 molecule of that makes 1 molecule of our desired product. So that means it's a one-to-one reaction. What does this tell me? This tells me I've got 0.00. If I carry this out properly, I'll make 0.0086 moles of the desired product with an MR of 72. So if I want to find the mass of that, moles times MR equals mass. So let's times that by 72, as it tells us right here. If you're wondering where I got the 72 from, it tells you right here that the product has an MR of 72. And if we carry out that in the old calculator, we will find out what the theoretical mass should have been. So we go 0.0086 times 72, and the theoretical mass should have been 0.619 grams, roughly 0.6192 grams. Okay, so now what I'm going to do is I'm going to move that theoretical mass down here, 0.6192 grams. You can see they've got quite a good yield here. What's it look? It looks over 80%. So it's a decent yield. Let's carry that out and see what that is. I mean, we could round that up to 0.62 to be honest with you, but there we go. 0.552 divided by my answer is 89.14%. So the yield here is 81.9%. And that's the percentage yield. That will have scored us at least 2 marks. Quite a bit of work there. Atom economy is actually a lot easier. So for this second part of the question, so this was the first part of the question. I'm going to use green for the second part of the question here. Calculate the percentage atom economy of method 2. So for atom economy, you need to know the equation as well, obviously, and it is desired products MR. It's not really the MR because you've got to use the coefficients. There's no well, there are some coefficients here actually. Divided by total products MR. And then we're going to times that by 100 to make it a percentage. Remember, atom economy, how well you carry out your experiment won't affect the atom economy. It will really tell you how much wasted product, how much side product you're getting and how much waste through the reaction. So here we go. State the importance. Oh, no. What we want to do is calculate the atom economy. So desired products here have an MR of 72 in method 2. You can see that right here. Here's the desired product. What's the total MR of water and that added together? In fact, you probably know from GCSE, what is the MR of water? Anyone who thinks 18, well, you've smashed it.
You absolutely smashed it.
And that's because the MR of water is 18. We've got 2 hydrogens, 1 each, that's 2. We've got an oxygen, that's 16, H2O. So the MR of water is 18. But look how many waters I have here. I have 2 waters. So we're going to divide that by 72 plus 2 times 18. So we should go 72 divided by what is 2 times 18 is 36 plus 72 108, so times 100 and we get 66.6% recurring or whatever. So 66.6%, and that's the second part of that question. So awesome. Right, let's move on. Let's do some other questions and crack through. So hopefully that helps you out. I advise working through the whole pack on Physics and Maths Tutor. You may have tests coming up for amount of substance. It's hours and hours of work, and you can check the answers. They have the mark schemes there. So, but I'm going through and explaining the answers. So yeah, groovy. And by the way, if these are helping you out, make sure you yeah.
If you push the button,
Like me.
Would you like it?
Like.
Right. Let's go. Where am I? Yes, this is a very hard question. So this is one that we, he says, is this a hard question? Boom, boom. It looks hard. Yeah, looks like a back titration, as they're dreadedly known. This is a titration where you want to find out the amount of something, concentration of something, or the amount of something in a sample, but you can't do a direct titration. Maybe because you've got a solid, and so you need to react it first so that you can get a solution that you can actually titrate against. So it's got 2 equations, as you'll see down here, that you've got to mess about with. So let's have a little look at this question. Let's get the highlighter out. A student does an experiment to determine the percentage by mass, so that's what we're going to be finding out, of sodium chlorate in a sample of bleach solution. So we're looking at trying to find out, I believe, what's the percentage mass of sodium chlorate within the bleach solution. And actually, if we come right to the bottom, use all the information given to calculate the percentage by mass of NaClO in the original bleach solution, and give your answer to 3 significant figures. And this is a 7-mark question, all right? So this is worth 7 big bad boy marks. So it should take you about 7 minutes without me waffling to actually do this question. So let's have a little look. Dilute a 10 centimeter sample of bleach solution to 100. Now that's important there that you read carefully. So we're diluting to 100. We're not adding 100 of water to the 10 centimeters we're diluting to. So we're adding 90 centimeters of water. We're diluting it to 100. You could already make a mess up there. Okay, transfer 25 centimeters, that's from the 100, to a conical flask and acidify it. Right, we've got to stop here and make a note. Okay, so this is what you should be doing when you tackle these questions in past papers and practice papers. We've got 100 centimeters of our bleach. We started off with 10 centimeters. We made it to 100 by adding water. That hasn't changed the mass of bleach in there. We've not changed the amount because we've just added water. We've not taken any bleach out. So there's the same amount of bleach in there. We've just diluted it, right? So we can do some titrations because we didn't have enough. We only had 10 centimeters. So we've diluted it to 100. We've then transferred 25 centimeters out. Now that is diluting it. By how many times are you diluting it? By how many times are you reducing the amount of bleach if you go from 100 to 25? Well, that's 4 times. So I want to make a note there because at some point when you see that, that's a trigger to think, right, let me write 10 times, 4 times, 8 times, however much they've taken out the original, because we're going to have to multiply that back up at some stage, and that's worth a mark. Right, going on here, add excess potassium iodide to the conical flask to form a brown solution. So we're adding excess potassium iodide, forming a brown solution containing iodide ions. Add 0.1 moles of sodium thiosulfate, Na2, S2O3 to the conical flask from a burette. So this is a titration until the brown solution becomes colorless. So then you've reached your end point, okay, and that's when you form iodide ions. Now we've been told the student uses 33.5 centimeters of sodium thiosulfate, and we've been given the density of the original bleach solution is 1.2 grams per centimeter, and we've been given some equations here. Okay, so yeah, this is a 7 marker and pretty tough. So the way to break these back titrations down, well, you really want to look for what can you calculate to start with. Think about moles. Start writing down your equations. If you're in a panic in the exam, one of the good things you can do is go, right, well, they're giving me volumes and concentrations. What equation do I know with volumes and concentrations? So you give yourself a minute to just calm your nerves. N over C times V. We've also been given something to do with mass because we've been given density there. You could write the density equation if you can remember it from GCSE. Density, density is mass over volume. So if I was to put that in a triangle, it's all a bit much, isn't it? And then if you're messing around with mass, you're probably at some point going to need mass over mR. So just by kind of writing down equations from the information you've been given, you might be helping yourself work your way through. Anyway, I'm going to go through. Hopefully you've already had a go at this question by the time I go through this. So let's go. I'm going to start at the bottom here. I've got 33.50 of sodium thiosulfate. Now, with these back titrations, you 99.9% of the time, you're going to be starting with the bottom equation, okay, and working your way back to the original equation. So this is an ionic equation, so they haven't bothered showing the sodium of the sodium thiosulfate. They've just shown S2O32 minus, so you'll have to be able to work that out. Be on your toes for that. And we've been told that there are 33.50 centimeter cubed of that. I need to turn that into decimeters. And we've also been given the concentration back here. Okay, we were given the concentration, which was 0.1, and that was of the NaS2O3, the sodium thiosulfate. So I can actually get back into this, and I can multiply using the equation over here. This top one, I can do concentration times volume. This is the volume down here, and I times it by the concentration, which is 0.1, and we're on our way to our first mark here. So let's grab that first mark of the 7 marks. If I can actually get into the blooming thing. Oh, do you know what? I'm just going to write it there. So it's cheese Louise times 0.10 mole dm minus 3. And that's going to give us our moles. So let's do 33.50 divided by 1,000 equals that times 0.100. And that equals 0.0035, or 3.35 times 10 to the minus 3. So you could write that times 10 to the minus 3. Lovely jubbly. Or you could write it as 0.0035. And that is of sodium thiosulfate. So that's scored our first mark. That's of the old Na2 SO3 Sugar Ray Leonard S2O3. Right, so we've worked out our moles of sodium thiosulfate. Now, why does that help us? Normally now when you've got moles in one of these titration equations, what we need to do is look at the ratio and see what we can do from there. So if I had, it says for every 2 moles of sodium thiosulfate, you're going to have 1 moles of iodine formed. So we can now work out our moles of iodine. Where am I? Okay, so we can now work out the 2-to-1 ratio. You might even get a mark for saying there's basically a 2-to-1 ratio to I2 iodine. So we can work out how much iodine we had. Why am I interested in iodine? I'm interested in iodine because it's the linking equation. Let me just rub that out, man. What I've done there. Right, it's the linking equation, the linking substance between the top equation and the bottom equation. So you can see the iodine that was formed in the first equation has reacted with the sodium thiosulfate in the second equation. So we're going to work out the moles of iodine. So we're going to divide that by 2. 3.35 times 10 to the minus 3 divided by 2 equals my moles of iodine, which is 1.675 times 10 to the minus 3, and that is moles of iodine. Cool. Well done if you're hanging in there, because this isn't an easy equation or an easy question, but you'll be scoring marks all the way and everyone can get these marks. So well done.
Boom!
Yeah, everyone can pick up these marks. So yes, this one's pretty hard. I have to admit, this this question's very tricky because there's so many small steps in these chemistry questions. But look, this is nothing harder than GCSE. That was just a concentration. You were given the information to get the concentration to start you off. So there's always a starting point where you'll get the information. And then from that, we use the ratio to get the moles of iodine. Now we know the moles of iodine. We can get the moles of bleach. Because if you look here, iodine is in a 1-to-1 ratio with the bleach. And you might say to me, sir, how do we know the COO minus is the bleach? They told us right at the top here that sodium chlorate is the bleach. And as they've given us an ionic equation and sodium's the spectator ion, we're not interested in that. Okay, my stupid Norton just popping up. Boom. Right. No. Stop. Yes. Go away. Yes. Ay, ay, ay. Sorry, guys. Norton messing around with me. Right, where were we? So we've got the moles of iodine. We now know there is a 1-to-1 to the bleach. That's the sodium chlorate. And as there's a 1-to-1 to the bleach, we now know that we have, cheese Louise, we have 1.675 times 10 to the minus, jeez, come on matey, times 10 to the minus 3 moles of NaClO. Okay, so we've got that many moles of sodium chlorate too. The only problem is that's in 25 centimeters. Do you remember I wrote the little times 4 there? Because here's where people will lose one of the marks. We've already scored 3 marks out of 7 now. Here's where we're going to pick up the 4th mark. We're going to multiply this by 4 because it asked us about how many grams, or what's the percentage mass of, well, the grams of bleach basically as a percentage in the original solution. So what we're looking at here for our 4th mark is to go, hey, we need to times this by 4 because there's 1.67675 times 10 to the minus 3 moles of sodium chlorate or bleach in 25 centimeters. But in the 100 centimeters we started with, there's going to be 4 times that. So we're going to go 4 times 1.675 times 10 to the minus 3 moles. And that is going to give us 0.0067. Let's just times that by 4. So 0.0067 moles in the 100 centimeter cube. Now, this is where people might make their first big mistake. They might think, hold on, I had 100, but we started with 10. Now I need to divide by 10. No. All of those moles, that 0.0067 moles, were in there. And we just added some water to it to make it up to 100. That hasn't removed any moles of bleach. It was once we only took 25 centimeters out that we then quartered the moles. So we're putting the moles back to what they were here in the 100. Now, next step is we've got to do how many grams what is the mass of the original bleach. So it tells us the original bleach was 10 centimeters. Check this out. We had 10 centimeters of the original bleach, and it's 1.2 grams per centimeter is the density. So if we do, we've got the volume and we've got the density and we've got the units centimeter cubed for our volume here because it's 1.2 grams per centimeter cubed. So if we use the density equation and do mass over volume, and we do 10 divided by 1.2, we do 10 times 1.2 because we've got the density and the volume, we'll get the mass. God, getting there eventually. So where's my face? Right, it's there. So we're going to find out the mass of the original bleach. So we go 10 centimeter cubed, which is volume. We times that by a 1.20 gram density. And we get 10 times 1.2. Even I can do that level of maths. That's 12 grams. That's the mass of the original 10 centimeters. Okay. Now we found out. Now we need to know what was the mass of our bleach. Well, the mass of our bleach moles times mR, so 0.0067 moles times the mR. What the hell is the mR of NaClO? Well, I'm sure you guys are cool with that. Na is 23.1, O is 16, and Cl is 35.5. So if we smash that all in, there's two NAs, remember. We've got 2 times that because it's NA. No, it's not. What am I on about? 2 NAs. There's no 2 NAs. Right. Let's just add this up, Tom. Don't be a plonker. I was thinking of sodium carbonate or something. 23.1 plus 16 plus 35.5 equals 74.6. So let's times that. Times that by 74.6 and we get, I think I'm dying here. It's late. I might have to call it a day after this. Right, we get 0.4. Oh, geez Louise, come on, mate. Sort it out, Tom. We get 0.492 grams. Okay, that's our mass of the bleach. So the final step for the final mark is to work out the percentage by mass. That was the original question, work out the percentage. So we're going to go, I'm using a bit of the next question, 0.492. We're going to divide that by the original mass of the bleach by 12, and then we're going to times 100, and we're going to pick up our 7th mark. So let's do it. 0.492 divided by 12 equals that, times 100. Bob's your uncle, Jim's your aunt. 4.1%. Might even be like 4.16% if I don't do all my roundings and stuff. Okay, so 4.1% or 4.16%. Yeah, as long as there's 3 significant figures there. All right. Okay. Cool. Do I want to do this next bit? I've written all over it, so we can't even really read it. It says the total uncertainty from the 2 readings. And the endpoint error in using a burette. So they're talking about the burette. Now, they used the burette down here. Okay, what did they use the burette for? Well, we got this is our result from the burette. So if you're wondering, 33.50 is the titration that was carried out in the burette. And this question is basically saying, look, the total error is plus 0.15. So that's for the 2 readings and the endpoint. What's the total percentage in total percentage uncertainty in using the burette in this experiment? So we need to do our uncertainty, which is 0.15, divided by the measurement. So we got 0.15 over 33.5. So let's try that. 0.15 divided by 33.5 times 100. It's 0.45. So once again, you take this uncertainty like we did in a previous question, and I divide it by the measurement, which in this situation was 33.50, and then times 100, and bang, it rounds up to 0.45. Okay, nice. I'm going to do 2 more questions, then hit the hay, as it's late. Oh wow, I just seen a message someone put on, but I didn't get back to them because I wasn't even looking at my live chat. Anyway, yeah, someone said, what made you start teaching science? Yeah, what made me start teaching science? I started teaching 25 years ago is when I started teaching at a school in Edmonton in London called Aylward School. So I started way long back, but I did my teacher training in East London in a school called Morpeth, and South London. Where was I in South London? I did my teacher training there as well. So it was like 20. That was like 26 years ago. So yeah, I've been teaching a long time. I don't know. I was a little bit clueless as what to do after university, which I think a lot of people who go into teaching are. Some people are just super inspired to teach. I was a little bit clueless, and I thought, well, while I was at my university course, I was always quite good at explaining. I wasn't the best student, but I was always quite good at explaining stuff to people. If they came to me and said, like, sir, not sir, obviously, they weren't weirdos, but if they said like, "Hey Tom, how do we do this? I don't understand how to do this." I used to be able to explain it, and I could explain it pretty well, even to students that got better marks than me. So I kind of just went, "Oh, I'm not bad at explaining things. Let me try teaching." And once I started, I loved teaching. I absolutely loved it. I'm not so keen on it now. Obviously, I grew out of the whole teaching in schools, so now I just do tuition, and this is a little bit of a hobby, a way to get in there and keep my brain ticking over. All right, last two questions. The equation below represents the complete combustion of butane. So I got butane plus 6.5 oxygen makes 4 carbon dioxide and 5 water molecules. 20 centimeters of butane are completely burned in zero point 0.2 decimeters of oxygen. Which statement is correct? And by the way, it tells us all volumes are measured at the same temperature and pressure. Once you know that you're dealing with gases and the volumes of those gases are at the same temperature and pressure, you can assume that the volumes are equivalent to moles. You don't even need to bother converting them into moles. So what does that mean? That means if I have, let's go through. So it says, is this statement true? 40 centimeters of carbon dioxide are formed. Well, how would we check that statement? How would we check A? A's not right, but I'm just going to go through how to check A. So we've got 20 centimeters of butane. That's C4H10. It then tells us that 40 centimeters of carbon dioxide are formed. Well, look at the ratio. What's the ratio of butane to carbon dioxide? It's 1 to 4. Okay, there's a ratio of 1 to 4. So we know straight away this is not correct. Because if I have 20 centimeters of butane, I should make 80 centimeters of carbon dioxide, right? I should make 80 of that. So this one is definitely wrong. Let's check the second statement. B says 0.065 decimeters of oxygen react. Well, let's check out that statement as well, right? We know we've got 20 centimeter cubed of butane. What's the ratio to the oxygen? Well, if we check the numbers out in this equation, it's 1 to 6.5. So if 20 centimeters of butane react, what's 20 times 6.5? It's 130. It means we're going to have 130 we're going to need 130 centimeters cubed of oxygen, right? Now, it says that's 0.065 decimeters. Is that correct? Well, if you do 130 divided by 1,000, it definitely ain't 0.065. So that's going to be wrong. Let's just see what that is. 130 divided by 1,000. Okay, that's 0.13 dm of oxygen, right? So that's not true. It's 0.13 decimeters of oxygen that have reacted. It then says 70 centimeters of oxygen remain. Well, we've just worked out that 0.13 decimeters of oxygen reacted. They told us here that we had 0.2 decimeters. So if you go 0.2 minus 0.13, we are left with 0.07 decimeters. Hopefully I've not just written over my face. Yeah, of course I have. Right, let me shrink that. Alright, so I now need to times this back into centimeters. 0.07 is sounding right, isn't it? Because there's a 7 in it. And that equals 70 centimeters. So the correct answer is yes, there would be 70 centimeters of oxygen left. That is the correct answer. Well, I'm going to do one more, then I'm going to finish because it's late. So, and yeah. Let's do this last one. The heat released when 1 gram of ethanol, MR46, thank you, undergoes complete combustion is 29.8 kilojoules. What is the heat released by each molecule in joules when ethanol undergoes complete combustion? So, first of all, they've given you Avogadros. What does this mean? This tells you the number of particles, right, in 1 mole. What is the heat released by each molecule in joules? So how much does 1 molecule of this ethanol release? They've given us the energy for 1 gram. First thing to do, guess what? Little trick, you've been given grams. What do you do when someone gives you mass? You find the moles, especially as they're basically telling you, listen, you need the moles, right? We're giving you mass, and 2 words later we're giving you MR. So we're going to do 1G, 1 gram, over 46 as the MR. And that's going to give us 1 divided by 46 equals 0.0217. And that's the moles of ethanol, right? That's some crusty ass writing. Now, we know the moles of ethanol. That gives out 29.8 kilojoules. So let's find out. That gives out 29.8 kilojoules in 1 gram of ethanol. And we now know how many moles we got. So let's find out what the numbers are of molecules. So we're going to times that 0.0217 by Avogadros constant. God, these things are long, man. 6.022 times 10 to the power of 23. So essentially, we're timesing the number of moles by Avogadros constant. And by the way, that's another equation for you. Moles times Avogadros is equal to number of particles. So you do need to know that as well. Moles times Avogadros equal to number of particles. And that's going to give us the number of particles. And the number of particles is going to be 1.309 times 10 to the 22. So that's how many particles were in 1 gram, or in that many moles of ethanol. That's how many particles were in 1 gram, and they gave out 29.8 kilojoules. So at this point, we want the answer in joules. Why do we want it in joules? Because all of these are in J. So we want 29,800 joules, and we're gonna find out by dividing that by 1.309, which is the number of particles we actually have in 1 gram, and that is going to tell us our answer. So 29,800, which is the energy in joules, divided by the number of particles in play. What am I doing? Times 10 to the 22. And it's 2.27 times 10 to the minus 18, which is 2.2765. So we're going to round that baby up, and that is going to be answer A. So that equals 2.2765. Let's stop it there, times 10 to the minus 18. And the closest answer to that is answer A. So there's our answer. All right, nice one. I am going to duck out there. Whoa. Yeah. Oh, shall I do one more question? One more question. Let me just see. Let me see. Oh, someone's put a comment up on the chat. How do I know when to use 24 decimeters or 22.4 decimeters? So when to use, when you're going to divide moles, when you're going to use that is when the temperature and pressure are the same. Okay, that's when to use 24 decimeters. When your pressure and temperature are the same, that's when you're going to use the standard 1 mole of any gas equals 24. But let's go on to another question.
Question, tell me what you think about
Chemistry.
Right, let's go. Let me do one more questione. So, I don't think I'll do this one tonight. I don't think I can be arsed with doing that one tonight. I should really. So, can I be bothered to do this question? This looks like a long ass question, man. I was hoping it was another multiple choice. I'm just going through the ones in order through physics and maths tutor, and this looks disgusting. So, okay. So, Mohammed, if you were still there. Sorry. Was that super loud? Yeah. Sorry, dude. Mohammed. So, when to use 24 decimeters is room temperature and pressure. However, when to use 22.4 is when it's 0 degrees and 1 atmospheric pressure, which is basically normal pressure. But the temperature is slightly different. So 22.4 apparently is standard temperature and pressure taken at 0 degrees, so the temperature is different. So when it's room temperature, it's 24 decimeters. 1 mole of any gas equals 24 decimeters in volume. And when it is when it's just normal, like in your room right now, it's 24. But if it was 0 degrees, it's 22.4. Cool. Sorry about that. Right, this question is disgusting. Okay, it's just a horrible one. But again, all of these questions I'm covering have been in the exams from 2016, so of the current specification. So they can potentially come up, but this one is absolutely horrendous. Okay, this question is about sodium fluoride. Some toothpastes contain sodium fluoride. The concentrations of sodium fluoride can be expressed in parts per million. 1 part per million represents a concentration of 1 milligram. I always say micro, don't get that M mixed up. Micro is the upside down U kind of symbol. So that's 1 milligram, a thousandth of a gram, in every kilo of toothpaste. You might not be interested in doing this question. I'm going to go through it and just smash out the answers to this question. But like, if you work through the physics and maths tutor questions, then you'll see what this question's all about. But yeah, let me go through it. Right. So you've got 1 gram of toothpaste. So if you put 1 gram of toothpaste on your toothbrush, it's been found to contain 2.88 times 10 to the minus 5 moles of sodium fluoride. Okay, calculate the concentration of sodium fluoride in parts per million for the sample of toothpaste. Give your answer to 3 significant figures, 4 marks. What's the concentration of the sodium fluoride in parts per million? Not our normal concentration, mole per decimeter. We're doing parts per million. And they're telling us, so it's kind of mental maths. They do this quite a bit in chemistry. About 10% at the A level is this kind of mental math stuff. So 1 gram of toothpaste found to contain that many moles. Calculate the concentration in parts per million. Cool. So first things first, I want to work out, I've been given the moles of sodium fluoride. What can we work out? I've got moles, which is 2.88. So I've got 2.88 times 10 to the minus 5 moles. If I times this by the MR of NaF, which is sodium fluoride, and what is that, by the way? What's NaF when it's in town? Sodium is 23.1 plus 19 for fluorine equals 42.1. So if I times that by 42.1 or 42, some people like, a lot of these maths calculations, you don't need to use the 0.1 for sodium. And that is going to equal times 2.88 times 10 to the minus 5. It's going to give me grams. It's going to give me 0.0012148 grams. Okay, that is the mass of sodium fluoride in this 1 gram of toothpaste. So we now know the mass of sodium fluoride in the toothpaste. Calculate the concentration of the sodium fluoride in parts per million. So what I want to do, I want to turn this into milligrams. Why do I want to turn the grams into milligrams? If I look here, it tells me that 1 part per million is equal to 1 milligram of toothpaste. So I want to find out how many milligrams of toothpaste I'm dealing with, how many milligrams of sodium fluoride I've got, then I can turn it into parts per million. So let's do 0.00122148 grams, divide it by, no, times, we're going down a scale, Tom. So we're going to times 1,000. When you go down, from like grams to milligrams, it's always counterintuitive. As you get to smaller numbers, you multiply. So like going from 1 meter into millimeters, you times by 1,000. So when I'm getting confused, do I divide by 1,000 or times by 1,000? I always go back to 1 meter, because then you go like, everybody knows, yeah, 1 meter in millimeters. Oh, there's 1,000 millimeters in a meter. So you'll kind of get that. Oh yeah, I've got times. So on the way down the scale, you always times. So we're going to convert this back into milligrams. So I think we're just going to dash 3 zeros there, and we're going to have 1.21248, and that's milligrams. So I now know how many milligrams I have of the sodium fluoride. So that's how many milligrams are in 1 gram of sodium fluoride. So that's in 1 gram. But in order for us to work out the concentration, it's got to be out of a kilo, because up here it says 1 kilogram of toothpaste. 1 milligram, 1 part per million represents 1 milligram per 1 kilo. So I'm going to times by 1,000 again. I know this is getting a bit confusing. So we're going to times by 1,000 again, and that's going to give me the how many milligrams if I had a kilo of the toothpaste. We've only got 1 gram, but we're trying to find out if we had a kilo, and it would be 121.48. Oh my gosh, 121.2.48 is what I've got. Milligram in 1 kilo. So the answer is going to be 121.48. Yeah, what's the answer in parts per million? That's a disgusting question. Now, the mark scheme for this might actually say something slightly different, like 1 to 10. It might say 1,210, because I stupidly you didn't look. I used the full units there. What have I done here? Okay. Yeah, I used the full units, which is a bit dumb. Yeah, this question's just horrendous. This is disgusting. Sodium fluoride is toxic in high concentrations. Major health problems can occur if concentrations of sodium fluoride are greater than 3.19 times 10 to the minus 2 grams per kilogram of body mass. Deduce the maximum amount of sodium fluoride that a 75 kilo person could swallow without reaching the toxic concentration. Alright, you're not allowed more than 3.19 times 10 to the minus 2 grams per kilo of body mass. So the maximum, so tricky. When you've got to read these questions, you have to bust out the highlighter. So, right, we know it's toxic. We know there are 3.19 times 10 to the minus 2 grams per kilogram. To deduce the maximum mass of sodium fluoride in micrograms that a 75 kilo person could swallow. Well, they could swallow before they die or get toxification, whatever that is, or they reach a toxic level. They could swallow 75 times that, but then we need to turn it into micrograms. So it doesn't really matter the order we do this, but they're 75 kilos. We're going to times it by 3.19 times 10 to the minus 2 grams. This is how much grams they can swallow, and then we're going to turn it into micrograms as well. So we need to times by 1,000 again. So let's do that. 75 times 3.19 times 10 to the minus 2 times 1,000. Can my calculator handle it? They can swallow 2932.5 micrograms. So that's how many micrograms of toothpaste a 75 kilo person. Sorry, that's how many micrograms of sodium fluoride. I was going to say that's only a teaspoon of toothpaste. I'd be like, what? Yeah, that's 292.5 milligrams, milli. That's 2,932.5 micrograms of toothpaste the person can of sodium fluoride the person can swallow, not the toothpaste. You can swallow more than a teaspoon of toothpaste without dying. So it says the concentration of sodium fluoride in prescription toothpaste is 2,800 parts per million. Use your answer to question B to deduce the mass of toothpaste in kilo a 75 kilo person could swallow without reaching the toxic limit. Okay. So it's telling us the concentration of sodium fluoride in prescription medicine is 2,800 parts per million. That's per kilo. The mass of sodium fluoride was... Oh, I wrote that in wrong. How did I got this number wrong in my calculator? What a D-head. Oh, come on, Tom. Sort it out, mate. It's late at night. That's what we meant. 2392. Okay. So what we want to do here for this disgusting question is move my face so I can work out. Oh no, I've got enough space. All right. So it's 2. Oh, Jesus. Jeez Louises. I want to go 2392. Gosh. 0.5 over the top of, what did they say? 2,800. And then we're going to times 1 kilo. Times 1. We know this is the amount it takes before someone gets sick. We know that's the concentration of the toothpaste. So, of the prescription toothpaste. .85. So you could have 0.85 kilos before it gets toxic. Quite a lot. Now for this final question, identify the diagram in the figure below that shows the correct relative size of the ions. This is totally not to do with what I've been doing with these calculations, but never mind. Okay, so sodium fluoride, the ions. Which ones are bigger than what? What? So when you're thinking about sizes of ions, you need to know about the nuclear charge. How many protons? So sodium, 11 protons in the nucleus, so has a bigger nuclear charge than fluorine. Fluorine has 9 protons in the nucleus. This means with more protons in the nucleus of sodium, it will have a stronger nuclear charge, and it's going to pull those outer electrons in closer, making its radius smaller. So essentially, our answer here, guys, is going to be B. I would expect the sodium ion to be smaller than the fluoride ion. Okay, you can kind of like follow with your finger across the periodic table. Okay, you can follow with your finger across. Fluorine's over here. What's fluorine? Period. Fluorine's in period 2. So you go there and then you drop down. Sodium's in period 3. So as you're going across like that, they're getting smaller as you go across. So you go that way because the nuclear charge, the amount of protons in the nucleus are getting bigger and they're pulling the outer shell in closer. Okay, cool. So that's the main thing. Increasing nuclear charge pulls the outer electrons in closer. I am definitely finishing there. This is a water crystallization. I'm going to pick this up in my next one of these. All right, nice one, people. Cover your ears because I am going to sound off. Oh, it's definitely time for me to hit the bed. I'm exhausted, so.
Okay, guys, it's late. Time for bed.
Yep. See you later. I'm out.
You're still here? It's over.